Thank you for joining, and thank you for being on time. Today's discussion is to talk a little bit about sequencing batch reactors and sort of the use of SBRs, and more importantly, how you can rapidly assess or generate designs for SBR technology. And we're specifically going to talk about SBRs in the context of our tool, Transcend Design Generator, which is a software that automates the preliminary design process for a number of different treatment technologies, including, of course, SBR. So I don't want to spend too much time on introductions, but my name is Adam Tank. I'm the Chief Customer Officer here at Transcend, was a member of the founding team. And we are always thrilled to put on these webinars, always excited to talk to people in industry. And of course, as you have questions, feel free to put those in the chat and we'll answer those as they come up. I'm now going to introduce Nicolette. She's a member of our team. She's a senior process engineer. She's far more technical and in many ways much more intelligent than I am. So I'm glad she's the one delivering this webinar today and not me. So Letty, the floor is yours.
Nice to meet you, everyone. Happy to see you in this webinar. So let me share my screen and then I will guide you through our tool and the SBR option of this one. So, okay, and here's my presentation. Okay, what we will hear, or you will hear today, is a short overview of the Transcend Design Generator, the tool itself, the structure, how it works, and then after that, I would like to focus on the SBR concept, the basis of the design, how we do in the system. And of course, I would like to show you the full user interface, including the SBR functions. So we will see how it looks like when it is working. And while the system will calculate the SBR system and do the design for us, I will show you what's in the black box. So we will go a little bit deep into the calculation, not very much, but I will just try to highlight the main points, what we take into account when we do the SBR designs. And after that, I will show you how our output documents look like and what do we take into account there, what kind of documents you will be able to download after the design is run. And at the very end, I will show a really mini feasibility study just to demonstrate the further capabilities of the tool, that how we think about it, how we think that it could be used for comparisons, checking different options quite easily and quite fast with our tool. So during the presentation, just feel free to write into the chat box if you have any questions, and Adam will guide the questions and I will answer them while we are there. So how our tool looks like, there's a user interface where you can enter all of your data for your project, what are the influent concentrations, effluent concentrations, you are allowed to do some site markings and so on. Of course, we have there some validations, so we try to make it not happening that you're entering unreasonable data. I will show some examples about this while during the user interface demo. When the data validation is passed, then the process design will take place. So we select different units for the facility, including preliminary treatment like screen, grid chambers, and so on. And then the main biology, the phase separation, tertiary treatment, and the sludge line parts. Each of the units are designed separately. And when all of them are done, in terms of process point of view, we are stepping to the mechanical part of the system, where we have an equipment database. And from that one, we do the equipment selection for each process unit. When this part is ready, then we are stepping to the architectural part, where we are creating a 3D BIM model from all of the previous outputs. So there will be a reactor and everything else placed properly on your site. And from this 3D BIM model, we also create the PDFs and some renderings for you at the document generation, which you can see in the right-hand side as the last step. So all of the previous information are collected into different documents. So from the civil, we create floor plans, site plans, civil BioQ. From the mechanical, we are creating equipment list, load list, and from the process, we are creating a process scheme and a technical description detailing all of the selected process units. So this is the concept. So everything is happening in the cloud, and you will just able to download all of the documents within a few hours after you have started your project. So the SBR is what we are talking about now. Is the sequencing batch reactor. So it's not a continuous system, as we all know. First, the fill cycle part is happening. We are filling up the tanks. If it is necessary because of the TN limits, an extra pre-react time is defined by the tool. So as an extra anoxic time can be added here. After that, the aerobic part is coming when the aeration system starts to push some oxygen into the system. After the reaction time, there's a settling where the solids are settling down. So from the top, we can remove the technically clean water. This is called as a decant phase. So this is what we are talking about now, and this is what is designed by the generator right now. Let me show it how it looks like on the user interface. Okay. So I'm just starting a new project. Oh, sorry, I was clicking on the wrong button here. We can add some basic project information here.
Hey, Letty, we have one question.
Yeah.
Can the model be, John asked, can the model be adapted to a continuous flow model?
Currently, no. The only supported SBR system now is the non-continuous batch version. That's, yeah, later on, it might be there, but now it is only the non-continuous version. Okay, so I was adding the project name. You can choose unit, metric, or imperial. I'm going with the metric one. I can actually move with the imperial. So let's do some location selection. So I'm selecting Hungary. And here's the option to select site without existing assets, select site with existing assets. I really don't want to spend some time on marking now, so I'm just going with the no site selected. In this case, the civil design will just pick up a rectangular shape as a site and place all of the units in that area. So this is the first main screen about the flow data and the temperature. Here we have defined some typical values for each of the regions which are available. You can accept these, but of course you can overwrite anytime if you have different values. So the design flow for the biological system is just, let's say, select some number. If we go here to the advanced button, we will have some additional flow data which can be set if we have the information. If not, then the system will not take into account any wet weather flows, because these two here, the peak daily flow and the peak hourly flow, are for the wet weather conditions. So these will be skipped if you are not providing the data. But if you are providing the wet weather data, then the system will calculate with the wet weather cycles when we can do faster cycle structures. We can go with faster cycle structure typically. So now I'm going with the basic one, just one design flow with the 10,000 cubic meters per day. So pushing the next one. Now we have arrived to the influent concentrations. Here again, we have some typical values given by the tool. So we can accept these, or we can just anytime overwrite it. I was mentioning that we have some validations for the influent concentrations. So let's say I was doing a typo and I have 400 for the COD and 500 for the BOD, and trying to move on. And the system will not allow this one because the COD is less than the BOD. So it was a very basic example. A little bit more higher level checks are also there. But yeah, just to demonstrate that we are trying to avoid that typos can go in. And the system would design something weird. So I'm just accepting these numbers now. And now it allowed me to move on. So regarding the effluent concentrations, again, we can accept what it is here. Regarding the nitrogen, we can go with the nitrate or with the TN limit. So you can switch and select which one you prefer. Let's say I'm going with ammonia of 1. So now we have added all the influent and the effluent concentrations. Now we are coming to the technology page where we can set some general preferences regarding the system. So the grid chamber type, whether we have this, the flow equalization question is not valid for the SBR because this is, as you can see here, we have some other technologies as well, which are supported. So the flow equalization is only available for the others. SBRs are always going with the flow equalization. Yeah, as I mentioned previously, that as it's always a non-continuous system. That's why the equalization tank is always required and designed by the tool. So I'm going with the SBR here. We can set the number of trains. If there no requirement is there, then the system will define. That's it. So now we have arrived the SBR specific technology page where users are allowed to set the cycle structure. It is worth mentioning that the user given cycle structure is just the guideline for the tool. The system will try to go with the given cycle structure, but if the system will not meet the effluent requirements with that given cycle structure, then these numbers will be overwritten. This is especially true for the fill time and the pre-anoxic time, because the denitrification requirements might overwrite these. Of course, if it's okay, then we are going with this one. But especially for this project, which I'm just starting with TN influent of 80 and an effluent of, I think I was adding 10 maybe. So when the denitrification requirement is quite high, maybe the 1 hour is not enough. So if you go only with the 1 hour fill time and the 0 for the pre-anox time, the system will increase it to make sure that the denitrification can happen properly and the effluent TN limit will be met. So these are just, I would say, target values for the tool. The minimum aerobic SRT can be also entered. However, if it is left empty, then the system will calculate. We can select biological phosphorus remover, yes or no. If no, then chemicals will be added. The MLSS at the top water level can also be defined. So let's say change it to 4,000. And the site elevation. The site elevation is used for the blower design. So that's why it is required to add it here. And that's it. So this was only what you have to enter on the user interface. And now, if we push the Run Design button, then the system will start doing the calculations. So I'm just hitting this one. And now we just have to wait. Typically, it's a few hours while it is ready. So doing all the calculations, all the equipment selection, all the civil drawings, the renderings, that requires time at the cloud to be ready. So yeah, until that time, the SBR button here is gray, but as soon as the system finishes, then it will turn to a blue button here. And if we click here, then we will see here the output documents. Okay, now let's go back to my presentation to see what's happening now in the system. So as I mentioned, the target cycle structure is allowed by the user. So it is really important to keep in mind that it will be overwritten if required. So you can play around with this, trying different combinations, but the system will always make sure that the limits are met. So you cannot really make huge mistakes, even if you enter something which is not enough for meeting the limits. Also regarding the equalization tank, it is always selected and it is designed together with the SBR tanks. In the next slide, I will show what I mean by designed together with the SBR tanks. And all of the calculations are done for the wet weather and for the dry weather cycles if the wet weather flow conditions are given by the user. The main process design at the background is an SRT and MLSS based process design. So as you have seen that the MLSS can be given, also the SRT can be given based on different yield values. We calculate the slush production as well, and this will lead to the required process volume. So how the equalization tank and the SBR reactor is designed together. Regarding the influent flow, even if you already only entered the main design average flow and nothing else, based on the population equivalent, we are calculating a daily flow fluctuation. This is just an example curve here, that how it will look like your one day so this is the full day flow variations of the influent one. And this curve is showing that how the pump flow to the SBR reactor is happening. So this has to be equalized by the equalization tank. So this differential equation in the top right corner. So the influent Q minus the pumped Q, this should be solved, and this is solved at the background by the tool to get the equalization tank sizes. So this is going into the tank, this is going out from the tank, and we are calculating what should be within the tank. In this specific case, for example, you can see that always there is a pump flow to an SBR reactor, which means that at least one SBR reactor is fed at that time. So here, when we are at the top, we are feeding 2 SBR tanks at the same time. But here, when we are a little bit down, then we are feeding only 1 tank. So all of these combinations that how the different trains of the SBR system are working together, all of these are calculated by the tool and taken into account when we do the design. So this is how it looks like when this equation is solved. So the equalization tank volume changes are shown in this graph. This is for 5 days. So we can see the top water level and the bottom water level part. So here's the bottom and here the top. So this is the curve which is showing us the required equalization tank volumes. Okay. So how the output documents will look like and what we are producing. So the first one is the process scheme. It's just high-level overview of each item of the system. So screening grit removal units. And in my example, I had 4 SBR zones, 1, 2, 3, 4 here, and an equalization tank before them. And in this specific case, only the UV disinfection here, so no specific tertiary requirements because the TSS was 25. This is also decided by the tool. So based on the TSS, if it is required, there's an additional microfiltration unit downstream the SBR system. And here are the sludge line parts. So the system decided to have a mechanical thickening and dewatering units and some slush storage tanks in between. There's a detailed technology description also created by the tool, where each item is detailed. So here at the very beginning, there is a summary of the influent and effluent flows. And as we go through, each units which you have seen on the process scheme are listed here with the main parameters like the number of screens, 2 duty, 1 standby, openings, the grit removal, also the different volumes, equalization tank specification, including the air requirements, and the details for the SBR system. So yeah, this is just an example where you can see that, for example, the field duration was set to, let's say, 0.7 hours. And this was defined by the tool because of the denitrification requirements for this specific project required only this amount of anoxic time. So that's why we could reduce the field duration. So the number of reactors and everything else is also listed. Process air demand and the UV disinfection unit, as I mentioned. Also, each of the sludge line elements are separately listed with the volumes, mixing requirements, number of units, and so on. As I mentioned that we are selecting the different equipments as well from our equipment list. So a detailed equipment list is also part of the output document set. Now I have opened it up in Excel. This is available in Excel as well. That's why I was using it now to show it. However, we are creating PDFs as well. But it is worth mentioning that all of our output documents are available as editable format. So if there's anything you would like to change manually, minor changes, then it's quite easy to do in those editable files. So here we have all of the units, blowers, centrifuge, thickeners, decanters for the SBR tanks, different pumps, polyelectrolyte dosing pumps, and so on. From all these equipments, a load list is also created with the different power consumptions, daily in and the final daily average consumed power values, and from which we are creating the total daily amount. And all of these are summarized in an OPEX table. So to make it easy and available, easily available for the users. So all of the OPEX related values are calculated, are shown in this one table. The electricity demand, the polymers, the sludge production, and so on.
Hey, Letty, John has another question around the sludge blanket level. So he says, do you have a sludge blanket level detector, as you don't want to decant if the sludge blanket is too high?
That's, I mean, within the system, we are having in the calculation that the maximum, what is the maximum amount of decantable volume. So we are counting in the process calculations that we cannot go very deep to do the decant. And in the equipment, that's not in the equipment list, but in the instrumentation list, that's a separate table. We have different instruments added, so that can be there if required. But as this is an algebraic calculation at the background for the process part, we only have a defined ratio, which is defining us that what is the maximum amount of decantable volume. If this is a proper answer. Okay, so actually this was the last, not the last, but the last from the mechanical part of the output documents. And there's one thing I would like to show you regarding the output documents. As I mentioned, that all of the editable files are downloadable. So here's the Revit file, which is created. So as I mentioned, we are creating these 3D BIM models. And this is how this facility looks like in 3D. So you can go in, zoom into each unit, check the details. And of course, if you download, if you have Revit, you can change the arrangement and everything how you would like. From this Revit file, we are creating different PDFs, of course, site plan, floor plan, renderings as well, and civil bioq containing all of the required concrete amount and everything which is required to put together a full civil bioq for the facility. So this is how it looks like in this three-dimensional drawing, which is also available. And actually, I was quite fast going through all of this very quickly. And there's only one more thing which I would like to cover here at this presentation, is this mini feasibility study, which I have put together prior this webinar. And what I would like to show here is that you have seen that within a few minutes, I was able to start a project. And as I mentioned, within a few hours, without any additional extra effort, I was receiving all of these documents containing lots of information about the possible project. And we can do the same for the same project with other technologies, for example, conventional activated sludge, MBR, MBBR. I was doing it for the same project. And did a small comparison here. So these are the outputs, the total reactor volumes for the different technologies, showing now quite obvious things, but of course, this is just a high-level comparison. And if you are interested in deeper questions, you can do even more designs with primary clarifier, without primary clarifier, with BioP, with chemicals. So all of the combinations can be checked and all of the different outputs can be compared. So now it was coming as an output that the MBBR seems to be the smallest in terms of reactor volume. However, it requires an extra clarifier. For the SBR, we had a quite higher reactor volume, but as we know, in this case, the phase separation also takes place in the reactor volume. So this is technically the reactor volume and the clarifier if we would like to separate it.
All right, Letty, we have a couple questions that came in.
Yeah.
So Steve asks, does the biological design account for return liquor loads on top of the sewage feed?
Yes, exactly. That's there. We are, as I have shown, that we are designing the sludge line part as well. So all of the flows coming back from the sludge line are incorporated into the to the load. Yes.
And then John also had a follow-up on the sludge blanket level detector.
Yeah.
So he said, so the answer that we provided, he said, not exactly, since if the plant receives a high FM or high load influent, you need the sludge detector to react to the higher biomass. One indicator is higher MLSS, but you may need to increase the RAS.
These kind of details are not incorporated now into this preliminary design. This is a preliminary design, what this system is doing. So we are not accounting for any extra stuff like this. So we are always calculating with just the given concentrations, given loads, and not taking into account these extra stuff, only the return from the sludge. So that's there. As worth mentioning always that this is a preliminary design with I would say basic calculations to have a basic design for different technologies, for example, to compare them, how they look like compared to each other, and so on. So that will be a little bit more detail.
That's it for questions for now.
Okay, thank you, Adam. So back to my comparison table. So yeah, also I was adding here the total hydraulic retention time, which is also saying that the MBBR and the MBR are the lowest here. I have added the column for the power consumption. So from the OPEX table, and it was quite easy to take these numbers. And we can see that they are quite in line, except the MBBR, because for the MBBR, we apply coarse bubble diffusers, which is quite much increasing the air requirements, so the blowers, and that's why the power consumption is going up. And for the sludge production, that also can be compared. And yeah, in this case, I was not doing different options here, only just the technologies. So the sludge productions are quite in line. But what other options can be taken into account, for example, is do with chemicals or with BioP. And in that case, you will be able to see the differences in sludge production as well when the chemicals are increasing the sludge amount because of the chemical sludge. Also together with the extra ferric, for example, as a chemical to be dosed. So all of these information can be put together in a table, and you can quite easily compare different options for your facility. And now this is a very new feature that we have the SBR in this.
Let's see, we have another question that came in. So Steve asks, can you add in if there is any existing capacity already?
Yes, that's there. So that's that's also there. As I have mentioned at the beginning of the user interface, I was not going with the marking there, but there is an option to select that you have existing site asset and existing assets on your site, and then those volumes will be taken into account. So the system will just calculate what extra you will need. Okay, so I think that's all from my side, what I wanted to share with you today. Do we have any other questions? Or anything else you would like to see, what I can show you?
Yeah, you're welcome to put them in the chat, or I mean, at this point, you're welcome to come off mute as well if you want to have a more nuanced discussion. Otherwise, some housekeeping. So we'll be sending out a link to register and use the tool. You'll now have design credits as part of attending the webinar. So you're welcome to run an SBR design or MBR, MBBR, IFAS, or any others. So that link is in the chat. You'll also be getting an email afterwards. But we'll stay on for the next, 10, 15 minutes or however long people want to talk about SBR. So thank you for attending. Letty, sounds like you blew people's minds. They're speechless. Thanks for joining, Sergio. Muito obrigado você. Our Brazilian friends, or Portuguese.
Hi, Adam. Thank you very much. Thank you very much, Nicolette. I was just wondering, when are we going to have a Portuguese version?
It's a great question. So we do have a Portuguese version, but it's for one of our enterprise clients. So it's not something that we've released to the public, but we are considering adding a foreign language translation into the public tool here in the near future. I can't give you any promises on timeline, but if that's something that you want specifically for you or your company, let us know. We'll talk about it.
Okay. Hey, thank you very much. Bye-bye.
See ya.
Bye.
Sam, thanks for joining. Yeah, plenty of updates over the last, even just a couple of months. It's pretty amazing, really, what the team's been able to do. Letty, I don't know if you see in the chat this comment John has. So it'd be good to be able to run the anoxic tank up front of the SBRs to see the anoxic time required and also see times for wet weather.
I'm not 100% sure I'm getting the question, because it is possible to set the anoxic requirements and the system will try to take into account. So, and also for the wet weather conditions, it is also possible to enter the cycle structure, the preferred cycle structure, and the system will check whether it is working or not and adjust. So, yeah. So it's technically there, I think.
Hey, any other questions? Again, feel free to come off mute or you're welcome to put it in the chat. Probably have another 5 minutes or so before we wrap up.
Adam, I don't know if you see that someone, Honey is asking if they have the presentation recorded. So will it be available for the attendees?
The answer is yes. Yep. We will send you that link. Great question. Okay, if there are no other questions, thank you all for your engagement and joining. Let's see here. Looks like John might have another, so Letty, feel free to answer that. But for everyone else, feel free to take off, and we hope to see you at the next one.
All right, just let me answer the question then here.
Sure.
So yeah, so you mean that see it upfront, I mean, on the user interface having some feedback, whether it's working or not. Yeah, this is an option which we may think about how we can incorporate any direct feedback there. But actually, this is quite a detailed calculations. And if we would like to do that, that would take some time waiting on the user interface for some feedback from the calculations. So I'm not sure whether it is technically great for user to sit down there and wait for some feedback. And that's why we recommend it in a way that you add one set of cycle structures, go away, do your other work, come back later, see how it was working. And there is an option to modify your project. So you don't have to enter everything again. But if you don't like the outputs, you can just click on the modify, change only, for example, the cycle structure, and run the project again. And again, you can do your work and see the results later on within an hour or two. So this is something what we recommend, just because it's easier for everyone, and you don't have to wait within your computer for the results. So PNID control loops, we are not providing now a full detailed PNID document. We are just selecting the equipment, and yeah, technically at the background, we have the controls connected, so we know where are the connection points, but the final PNID is, as a drawing, is not available now. We are working on it, and it will be there with all of the connections, but now it's unfortunately not there yet. We have another question. I think, Adam, you don't see it because it seems to be a direct message to me. Okay. Again, from Honey, that how we decide if extra anoxic anaerobic tank is required or not. We have algebraic calculations based on the nitrogen influent and the nitrogen effluent. We calculate how much denitrification should happen. We also know from this is all of the calculations and the ratios and things like this are from public literature, mainly from Metcalf and Eddy textbook. So we are taking there the typical denitrification rates, and from that we calculate the required time for the nitrate to be denitrified, and this will give us the required total time for the anoxic and anaerobic parts. And that's how we just do the check. So we calculate always that what the system is would need based on these numbers. And if the required numbers by the user are less than this, then we adjust to make sure that the required time will be there. If the user requires higher, then we may allow to have the higher, because those don't have wrong effects on the system. So on that part, we can rely on the user input. Regarding the anaerobic, that's a little bit different. Yeah, for that one, we also have a calculation based on the anaerobic mass fraction requirement. We had another presentation webinar regarding the BioP, so that has details on how the anaerobic part is calculated exactly. But that's also the same algebraic calculation in the background, or very similar.
Do you see that next question?
You mean, does the anoxic zone is separate, or it is included in the volume of the SBR when filling time? It is included in the SBR. So the fill time is considered as anoxic or anaerobic. And if required, after the fill time, we have a dedicated pre-anoxic time as well. But yeah, that's only one tank. So it's a really conventional basic SBR, which is implemented now into the tool.
All right. If there are no other questions, this is the last chance, so speak now or text now. We're happy to answer them. Otherwise, we're also available, over email, website, etc. I'll put my email address in the chat for anyone that wants to reach out. And of course, we'll be sending you the link to the recording as well as the link to register for the tool. So thanks again to everyone for joining, and hopefully we'll see you on the next one.